Hello, everyone. Can you guys hear me good? Yeah. All right. Okay, so I guess we can get started. Let's start off maybe with who am I? Why I'm here speaking to you guys about DuckDB, right? So I did my PhD in database architectures at CWI. Is anyone here from the Netherlands? Oh, so I'm going to butcher your language a little bit. I'm sorry. So CWI is the Centrum Wiskunde in Informatica, which is the Center of Mathematics and Computer Science in Amsterdam. And it's actually the place where DuckDB was born. So DuckDB was born in the database architectures group. Also, CWI is where Python is born, in case you didn't know. So there you go. Also, the first point of internet in the whole Europe. So it's quite a strong research institute in Europe. So I did my PhD there in the index structures, and while doing my PhD, I was already working at DuckDB. So you can see there on the GitHub history, it was basically the co-creators of DuckDB and me on the first July to August of 2018, so long, long ago. So today, I'm a software developer at DuckDB Labs, which is a company that maintains and continues development in DuckDB. And I did all kinds of stuff. So, of course, I did my PhD in indexes. So, first thing I did in DuckDB was an index. I did zone maps. I did Arrow, ADBC, substrate integration. Maybe you guys heard some of these words earlier today on other presentations. The main reason I'm here is because I did the big chunk of the Python API. I'm not a Python guy per se. I'm a C++ guy. But I did my very best. And I'll show a little bit of that to you guys today. Worked on the CSV reader and tons more of other stuff. So a little bit of the outline of the talk today. I'm going to go quickly over motivation, so really about database systems for data science and data analytics. Talk about the alternatives, so classic server clients and data frame solutions. And then, of course, going to talk about in-process database management system, specifically DuckDB, and what makes DuckDB so special. So what were the design decisions there that make it different from all these other solutions? Of course, this is a Python conference, so I'll talk about DuckDB in the Python lands, our integrations, what's our usage, the different APIs we implement, and Python UDFs. I'm going to do a little demo and then finish off the talk. All right, motivation. So this is a classic data science workflow. So usually in data science, what you do is you start off by exploring your data. You have a question in mind, and then maybe you zoom in on a piece of data to try to investigate if your question or your hypothesis is correct. You explore it, you model it. Maybe it's like suddenly, OK, this is wrong. I'm going to analyze something else entirely different. And you kind of keep repeating this process all the time. So if you think about the workflow, it's simply that. Ask interesting question, get the data, export the data, model the data, visualize the data, repeats. If we think about the libraries that are part of this workflow, we can think of asking an interesting question, exploring the data. These are basically queries, right? We're actually trying to get pieces of our data and then model it with, for example, TensorFlow or PyTorch and visualize it with Plotly or Matplotlib. And the data comes in all shapes and forms, of course. Nowadays, you have JSON files, CSV files, Parquet files. You have binaries from other database systems. But the interesting thing here is that in two important pieces of this workflow, we need a database engine. And this database engine, as we've seen previously, must scan all these different file formats, right? So file comes in all shapes and forms. It must integrate with ecosystem tools. So if you think about these machine learning libraries, if you think about the plot libraries, they're frequently well available in Python, but you need to be able to get your data in and out to these tools. And it must be efficient in executing analytical queries. Data science, data analysis, these are analytical queries, and you must ensure that they go beyond memory execution. There's nothing more frustrating, for example, if you're running your query on your computer, and just because your data doesn't fit in memory, bam, the whole thing blows up, right? It must also handle complex query optimization. And what I mean by complex query optimization is not only filter pushdown or projection pushdown, but also subquery flattening, for example. And one thing we also noticed is that there was a talk earlier on talking about a relation API and SQL and how they differ and the benefits of each. what we notice is that people usually use both of them in different parts where they fit most. So these database engines should be able to support these two things. And when we start to see about the alternatives of how you could do data science, you can think of course, classic server database systems, relational database systems like Postgres, SQL Server, Oracle. Years of database research embedded into them. Like I'm talking about 40, 50 years. So they have a full-on query optimizer. They have a buffer manager, so they can do data that does not fit in memory. They have their own storage, so they can apply compression and have everything in one file. They have a state-of-the-art execution engine. They support SQL. But I have a question for you guys. Has anyone ever managed to set a Postgres instance, for example, in less than 5 minutes to read a Parquet file? 2 people? 3 people? More or less, 10 minutes maybe. It's tough. It's difficult to set up. So it requires upfront schema creation. You need to know exactly what your data looks like. It doesn't have any integration with an analytical ecosystem. So if you want to then transfer your data to, I don't know, TensorFlow, for example, you're going to have to write something that queries it and that transforms the data there. And the way this works when you think about Python is the figure. Do I have my mouse here? No. It's the figure down there. Like you have your relation database system, you have your Python analytical tool, but your whole data needs to go through the database connector. So basically you're copying and transferring this data. This becomes a huge bottleneck. So that's a no-no. The other solution is data frame libraries. They're pretty cool. I mean, everyone here uses like Pandas, for example, right? It integrates with these ecosystems very well. They use like NumPy or PyArrow underneath. Very easy to use. With Pandas, you can read the CSV file in one line. You don't have to set up a schema. All the magic happens for you. They have a relation API, fast data transfer because they're running the same Python process. So usually they integrate so well with these other libraries because they also talk NumPy or PyArrow that you don't really need to do any copying. And as I said, like with the CSV files or Parquet or whatever, they have so many integrated scanners for all these file formats with the schema detection with automatic schema detection. Well, the problem of data frame libraries is that they are not such great analytical engines. So usually they don't support SQL or support just a small subset of SQL. Usually they have no query optimization or only simple query optimization, so no subquery flattening, for example. It's frequent that there's no beyond memory execution, so if anyone here, again, used Pandas before, you know if it goes over your memory, the whole thing burns, your Python process dies, and that's it. There's no storage, so basically you're going to be still handling whatever, CSV, Parquet files, a bunch of them, bunch of hard-coded path, becomes super cumbersome. In the case of Pandas, for example, there's not zero parallelism, like everything is single-threaded, so it doesn't matter if you have a shiny new MacBook, it's still just going to be one thread. So we decided to, okay, we kind of want to do something like nice as data frames, like easy to use, pleasant, people enjoy it, but with everything we know from academia, all the cool stuff to make analytical query engines good. But where can we draw inspiration to something that's like a database system, but kind of similar to data frames? And that was SQLite. So SQLite is an embedded database system, so it runs in process. There's no external server management, so you don't have to do any of the setup that a Postgres has. It has basically bindings for every language. The storage of the database is one single file, so it's easy to transfer. Public domain, super easy to use. It's actually secretly the most used RDBMS in the planet. It basically runs on every cell phone, every browser, even airplanes. So it's great. The only problem is it's built for transactions and not for analytics. So that's kind of like where DuckDB, the idea was from. So we want to do something for data science that works very well with these analytical tools like Python and R, so very well integrated, zero copy. That works with data visualization, that's small and can be put in any sensor you want, for example, and still a very strong execution engine for BI and analytics. Doing resource sharing, because of course you're running the process, so you need to be able to communicate with the other processes, and again, with the fast data transfer. And that's, of course, the beautiful table where we have like data frames, client server, SQLites, they're all lacking something. DuckDB has it all. And I'm going to show you guys a little, like I'm going to give you guys a crash course on database systems in a bit. All right, DuckDB. So as said, we wanted something that was easy to install, simple to use. To install DuckDB in Python, pip install, no big secrets. It's embedded, so there's no server management. It runs within the Python application. Has fast analytical processing, has this fast transfer, supports full SQL. So our parser actually was the Postgres parser. It's a single file format. It's free and open source under the MIT license, which I think is the most permissive license out there. We're currently in pre-release, so our version now is 0.8.1. You can, of course, check the website for documentation and more details about this. So let's do a quick crash course on database systems. I'm going to go each of these topics of design and try to explain like what makes DuckDB different from, for example, SQLite and Pandas. So when you think about data layout, you basically have two ways that you can store your data. You can either store your data from your table contiguously in memory per row or per column. So SQLite has contiguously per row, which means that if you think about the memory, you're going to have first the first row, then the second row, then the third row, so on and so forth. That's pretty nice because individual rows can be fetched very cheaply. So that's very nice for a transactional database system, for example. And it's particularly nice when you don't have a lot of memory because that means you only need like one row in memory per time. But the problem is if you have a wide table and you're not actually using all the columns, you're still going to have to fetch all the columns. So for example, if you're not only interested in the price of a product, in our example here, but not the stores in which the product is sold, that still means you're going to read the whole table. The other option, which is a column storage, so basically any analytical database will be a column storage these days, DuckDB or Pandas. We can actually fetch these columns individually because now the columns are stored sequentially in memory. And then this brings immense savings on the disk I/O memory bandwidth when you're only accessing a few columns. So again, if we have the same query where you're only interested in the price of a product, we would have the products, here's not the data and stores. Yeah, so basically we have products, consumer, and price. So then this reduces already the number of columns we would be reading from here. So if we get like a bit to the numbers, let's say we have a 1 terabyte table with 100 columns. We have a query that just requires 5 columns of this table. In the row stores or in the SQLite, Postgres, you're basically going to read this whole terabyte from disk, which at 100 megabytes per second is about 3 hours. And where in the column store, that means that you only actually need to read these 5 columns, which is 50 gigabytes. That reduces the time for 8 minutes. The other nice thing of actually having a column database is that you actually have the values of the columns again sequentially in memory, is that the columns usually have similar values. So for example, dates are usually increasing, and that means you have more opportunities to apply compression. So here in this table, I have DuckDB from version 0.2.8, so that's July of 21. There was no compression, and then we implemented a bunch of stuff. So we implemented constant compression, we implemented repetition, we implemented bit packing, we implemented compression for strings, for floating point numbers. So in about a year and a half, we managed to reduce, for example, line item, which is a classic table from a database benchmark, up to 5 times. And the taxi dataset's pretty classical for data science, up to 3 times. So exactly by taking this leverage of the similar data being stored. So if we go back to our example, that we only required the 5 columns from the table, which were 50 gigabytes and took us 8 minutes. Now by applying compression, so about like 5 times of savings. Of course, this depends on your data types and all. This time can already be reduced to 1:40. The other thing that I can talk about, of course, is the execution engine. So SQLite uses what we call tuple at a time processing. So it processes 1 row at a time through the query plan. Pandas uses a column at a time processing, which means it processes entire columns per time. And DuckDB uses this technique that was actually created at CWI called vectorized processing, which processes batches of the time. So not really rows, not really columns, but small pieces of your table. So if you think about the tuple at a time, again, it's optimized from when you didn't have a lot of memory in your computer. And that's because throughout your query plan, you only really need to have 1 tuple at a time. However, because you always passing this one row per operator, you always cleaning the caches of your CPU. So it creates a huge CPU overheads. So basically, when we're executing a query, we go row by row, query process results, so on and so forth. On Pandas, because you're doing column at a time, you already have better CPU utilization. So for example, you could do SIMD, single structure, multiple data. But the problem is that you have to materialize the whole column into memory. So if you don't have a lot of memory, you're going to get into trouble, because these intermediates, of course, can be gigabytes each. So again, the example is that would process one column, the second column, and then get to the results. DuckDB, again, is the vectorized processing. It's optimized for CPU cache locality. It still allows for SIMD for pipelining. And the whole idea is that you have these intermediates ideally fitting in L1 cache. So for example, you would have like the first chunk being processed, getting the result, the second chunk being processed, getting the results. I'm not so sure how familiar you guys are with modern CPU architecture, but basically you have the CPU core, and then you have these caches up to the main memory. And the difference of them is that the cache is closer to the core, they're smaller, but have a very fast access. And further from the core, they are bigger, but they have a higher latency. So by fitting your data in L1, which is the size of these batches in DuckDB, you're basically paying your latency of 1 nanosecond. It's pretty fast. But if you think about your data from Pandas, well, it's not going to, we're talking about gigabytes of data, right? So that's not going to fit in L1, not going to fit in L2, not going to fit in L3. It's going to end up in main memory. So then suddenly, for every time you're accessing some piece there, you're paying this huge difference in latency. And that's where this bottleneck in execution engine comes from. My computer is not, yeah, cool. So the other thing I talked about, of course, was query optimization. So DuckDB does all sorts of stuff, does expression rewriting, does join ordering, subquery flattening, filtering projection pushdown. And here I have an example of how this is done automatically in DuckDB, but manually in Pandas, right? So basically, I have a table here with 5 columns, A, B, C, D, E, and I'm getting the minimum of A, applying a filter in A, and group it by B, right? So what we can see here in the DuckDB plan, furthermore to the right, is that in the scan of the table, we are already pushing down A and B in the projection. So basically, we're like, OK, this table has 5 columns, but we're actually only interested in these 2. So just go with these 2 up to the plan. And then if we go to Pandas, where, for example, we start off by filtering our data frame, so getting the values from our data frame where column A is bigger than 0, and then doing the group by and the aggregation, that means on this filter data frame, you're not pushing down any projection. You're going to basically go through your whole data sets. This type of optimizations, they need to be manually done. DuckDB, again, has parallelism, so it has parallel versions of most of its operators, scanners, aggregations, joins, and scanners. They can also be insertion order preserved, so basically it guarantees that the data will be output in the same order it was inserted. So here I have an example of an aggregation of TPC-8 score, classical benchmark for database systems, on the scale factor 10. So basically what you can see from the charts is that the more threads you're putting there is actually going down quite nicely, which means the parallelism is working very well. It also has the beyond memory execution. So it's not only because your data doesn't fit in memory that everything should burn down to the ground, right? So you kind of have this never give up, never surrender mentality. Doesn't matter if it's going to take a little longer, we're going to execute your query. At least that's the goal. So we want to support this also with graceful degradation, right? It's not, oh, oops, doesn't fit in your memory for 1 megabyte, now it takes way longer. No. The less it fits, of course, the more impact it will have, but it's not going to be a huge spike. So here, for example, I have a hash join. On the x-axis, I have a memory limit in gigabytes. The data itself fits in 10 gigabytes. And then we can see that, OK, the time is going up, but it's not drastically going up the less memory we have. So Python integrations, well, we actually integrate with the Python ecosystem, I would say, quite well. the thing that we ourselves did here very strongly was to integrate with these data formats. So when you think about NumPy, Pandas, Arrow, Polars, and PyTorch, we really try to have zero copy integration with them, which means that we can transform, for example, two Pandas and read Pandas data frames without copying any data. TensorFlow, that's not really true, but we still integrate with TensorFlow. And then all these other libraries, for example, the IBIS project, the data frame API, we're actually the default execution engine of IBIS as well. Yeah, the slides more for reference. A bit of usage. So this is the amount of downloads DuckDB had on the last month. So that's about 1.3 thousand. This is only for the Python clients, which I think it's still our biggest clients. Again, we have clients for many different languages. But that already gives a feeling that it's a project that's maturing quite well, that's been quite used. So we have over 11,000 stars, over 200 contributors, and it's used by over 3,000 projects on GitHub. APIs, we do support the classic Python DB API, so where you create connections, you create cursors, you execute your queries, you fetch results, so on and so forth. We have a relational API that's more inspired by Pandas. So you're going to basically be able to, in this example here, you have a connection, and then you can create a relation that points out to a table in DuckDB, and then you can start to chain operators, right? So you have, okay, this table relation, I want to apply a filter, I want to apply a projection, so on and so forth. So it has a look and feel similar to data frames. And we also have the Spark API. So the idea of the Spark API is that it's going to be one-to-one with the actual Spark API. It's still a work in progress. Yeah, if anyone wants to contribute to that, you guys are also very welcome. Last but not least, Python UDFs. This might be too small for the people in the back, unfortunately. But the idea here is that you can actually have Python code that can be executed directly through SQL. So in this example here, I'm basically creating World Cup titles. So it's just a dictionary with the name of a country and how many times that country won a World Cup. Then I create a function called World Cups. It basically just do a lookup on the dictionary, so very simple Python function. But I can register that function in DuckDB with a name, and I just have to give like what's its inputs and what's its output. So in this case, it's just a varchar string, and then it's going to output an integer. And then I can create a table with countries. So for example, Brazil, Germany, Italy, Spain, Netherlands, and I can apply directly that Python function via SQL. So of course, this example is quite simple, but you guys can imagine about doing machine learning via Python UDFs. And then after applying it, of course, you have the results with Brazil with 5 World Cups, Netherlands with none yet, but maybe in 2 years. Now let's go for the demo. All right. Is this good enough for the people in the back? No, yes, no, bigger, like this? That's good, cool. All right, so I start this example here by uninstalling, so this is a collab. And DuckDB and Polars, for example, they are already shipped with collab. So I actually uninstalled them and installed them again just to show you the sizes of these libraries. I download then 3 data sets, so it's basically the cab data sets. So it's the cab rides from New York from January of 2016. I get the weather in a CSV file for that month, and I get a JSON. So that's basically it. So here, what I want to show first is that DuckDB has about 15.9 megabytes, so it's quite a small library. When we look at Polars, it's 19.1, it's a little bit bigger, nothing too crucial, too crazy, but when we look at Spark, that's 310 megabytes, so that's like 20 times bigger, so I expect 20 times better performance. I think that makes sense, right? So when we go here, for example, to just execute a SQL query in DuckDB, you can import DuckDB. You can just do a DuckDB SQL with the SQL you want to execute to show, and you already have your results. Again, DuckDB can read from all these different file formats, right? So for example, we have a from CSV auto function that we just pass the CSV path for the file, automatically detects all the types, column names, and reads the CSV file. we can do the same for Parquet files. So DuckDB has a from Parquet function. You pass a Parquet path, does the same thing. Automatically, it's completely able to read that Parquet file. And we have the same thing for JSON. So when you pass a JSON path, again, with a read JSON function, it can just read JSON files. So it's very well integrated with all these different file formats. We can also read Postgres database files and SQLite database files directly. So we can also create DuckDB tables from these files. So in our example here, we're creating a database from DuckDB called rdb.db. And we're basically creating the table CSV, JSON, and Parquet, selecting all the data from each of these paths. And the Parquet file specifically is quite sizable, so you can see there's a nice progress bar going on there to tell us when the data is fully converted to the internal DuckDB formats. A little bit more. Collab machines are for free, so I can't complain. Yeah, it's done. And then the nice thing of this is that we can connect against this database that we now just stored and create relations from this table. So we can create, for example, a CSV relation that points to the table CSV that we created here, right? And then we can get the relation and use two CSV. So we can now output CSV files as well. We can do the same thing with the Parquet. We can go and point to the Parquet table we just created, and we can use the toParquet function, and then we can output a Parquet file. So we can also input and output these data formats. So let's go for a very quick performance comparison between Pandas, DuckDB, and PySpark. So here I'm just importing the libraries. Here, I just want to show like how big the New York City data sets is. So it's basically a table with multiple columns of different formats, integer 64, timestamp, doubles, and whatnot, and has 10 million, almost 11 million rows. So to benchmark this, of course, we want to have some kind of time function. So this is basically running the same thing 5 times and getting the mean time. And we're going to do everything from data frames. So I'm not going to give DuckDB the advantage of having the data in its own formats, but we're actually going to go through Pandas data frame. So we create a data frame by reading the trip data Parquet. It's reading it. All right. So then the query you're going to execute is actually rather simple. We just want to the passenger count, the average trip amount, for short distance, so they're under 5 miles, grouped by the passenger counts. So basically, we want to know how much money our cab drivers getting from tips grouped by the number of passengers. So we can run this in DuckDB. And then this takes about 0.29 seconds. And because DuckDB can also, again, output back to a data frame, and that's what we're returning here as well. We're consuming a Pandas data frame and returning a Pandas data frame. We can also use like the nice plots function from Pandas. And then we can see here, oh, maybe this is too big, the number of tips per passenger. The interesting thing here is that 0 passengers is actually getting quite a sizable tip amount. Not sure what's going on there, but it's New York, you know. I don't know. Then we can run the same thing with Pandas. So again, Pandas is just reading its own data frame, executing the same query, but using the Pandas API. And it's going to output the same plots. So now it took 1.7 seconds, quite more than DuckDB. And again, remember, this is a machine that's not very powerful, right? It's a Colab machine. If you run this on your MacBook, this difference will be more drastic. And then we have basically the same plots. And now we're going to run it with Spark. So actually with Spark, I tried to run it through the data frame, but it actually crashed my Python process. So I had to allow Spark to be able to execute it by creating its own data frame through a Parquet file. Otherwise, I couldn't benchmark it because it was crashing my Colab machine. So this is running. Yeah. You guys want to talk about something? Yes. Yeah, so of course, I would say that queries like this are not exactly data manipulation, right? Like you're actually applying it's a proper query, but it's a simple query for the purpose of the example. But you can use it basically whatever you want. So you can use it, we really designed it with the local machines in mind. So our initial goal is we want users to be able to get the max of their laptops, but you can totally put this on a server. And we actually have a sister company called MotherDuck that's actually doing DuckDB for the clouds, but starting from your laptop. So the premise is a bit different. You only grow when you cannot fit things on your laptop anymore, and then you start paying the cloud providers. So Spark finished, so it's 3.5 seconds. Yeah, so I guess all that size didn't really help them on the time. More megabytes, more time apparently, yeah.
Time is 0 to pi.
Sorry? All right, so quick summary. DuckDB is an in-process database system. We really focus on this fast data transfer. None of this dedicated server hassle. All the goodies from analytical DBMSs, so really empowering the users with all the cool stuff the academia has been doing for the past 50 years. It's really designed for analytical queries, so think about data analysis, data science. Again, it's open source, under MIT license. If anyone wants to take it, fork it, create another company, make money out of it, feel free. You can do that. It's completely free to use. Has binding for many languages, so here I showed Python, but you have R, Java, JS, Go. If there's a language out there, we probably have a binding to it. Very tightly integrated with the analytical ecosystem, so from the example I showed you, we can even read data frames and be faster than Pandas playing their own game, kind of. And it has full SQL support. Last but not least, I actually brought some, I only had this here so I wouldn't forget, but I have some keychains and stickers. Guys, please don't let me go home with this. I hate to bring swag back, so after the talk, come here and pick some up. Thank you.
Thanks, Pedro, for a good session and probably making ducks out of our databases, if we can say that. So yeah, we have a few minutes for quick Q&As. And for that, you'd have to come to the microphones that are here. And yeah, thanks.
Hiya, thanks for the DuckDB. We love it. We are using it with lambdas. We have so many lambdas. We split the problem into many pieces. So our quants are relying on so many group by operations. And you know, lambda has a limit, AWS lambda, in memory-wise and temp memory-wise. And I think group by is depending on many temporary storage in DuckDB. Can you suggest anything to overcome with the memory issues when we are having group by operations?
So I think recently on the last version there was more work done in the, so with memory issues you mean it's crashing because there's not enough memory? It's just, okay. Yeah, so I think on the last version we had more work on out-of-core group bys. I'm not sure exactly which version you're currently using.
If I'm not wrong, F 0.1, we pinned that. If I'm not wrong.
0.1 is quite...
0.61?
0.61, yeah, that's already quite old, I would say. So there had already been 7.71, 8.81, like 4 releases after that. So okay. I would suggest you try the latest version.
Okay, thank you. Cheers.
Thank you.
Other, thanks so much for the great talk. So we usually deal with a situation where we have effectively like a DAG of expressions, so like a kind of a root node of the first expression, and then we have like derived expressions from that. You could express that as multiple SQL operations, for example. Do you think it would be sensible to use DuckDB with multiple SQL operations, effectively to create like a tree of expressions. Would that be like lazily evaluated somehow, or does that make sense?
Even if you, so I'm not exactly sure how your expressions are implemented in that case. Are you using something like a data frame already? Or, because even if you use the DuckDB relation API, the relation API, it doesn't really execute the query when you chain operators. Yep. So it creates a query plan that's actually only optimized and executed when you reach certain comments. So for example, when you try to fetch results, it's like, all right, so now is the point that you can actually get the query and really go through the optimizer, which, yeah, will do unchaining or something like this and get a good result for you. So you should totally be able to do that.
So just a quick follow-up. So then it would probably like still already work for our use case if we just like try to use it, I think so. And then if the data changes on disk, say, you would need to recompute and you would effectively have a new query plan. You would have the same thing happening again, right? So you say a part of the data changes in a file on disk, say in a Parquet file, for example. Would that be a fast operation, or
if the data changes in a Parquet file, you have to reread the Parquet file.
Yeah.
The DuckDB itself, it supports updates. So we do have MVCC implemented, kind of like an MVCC for analytics. So if you're using the DuckDB formats, that would be quite fast, I would say. But if you're doing updates somewhere else and then outputting a new Parquet file, you have to reread it. No way around that.
No, perfect. It's really good. Thanks.
Cheers.
Hi, thanks for the talk. I was just wondering if you could explain a bit the relation between Substrate and DuckDB.
Between Substrate and DuckDB?
Yeah.
So we actually have support for substrates, but we don't use Substrate internally in any way. There are some other database engines like Velox, for example, that I think uses Substrate as their actual query plan. What we do is we have an extension that allows users to read from substrates and to output substrates. But that's not really used internally in any way. I know there are some users and clients that use it. What I can tell you about the current status is that we can round trip most of the TPC8 queries. So there's still some problems with correlated subqueries, for example. And we can work some queries as well with IBIS, for example, but it's still very much a work in progress.
All right, thanks.
Pedro, thanks for your talk, and thanks for DuckDB, which looks like a very promising thing out here. I've been playing with it and having very good results. So the question would be, we're at release 0.81 or something. What would the DuckDB team call 1.0 release? What would be the conditions, assuming that 0. something is not stable and 1 would be stable, and that's my assumption.
Yeah, so I would say that it's not that the execution engine is not stable, or that, like, I think it's quite well tested by now. What we would call the 1.0 is when we have consolidated storage formats to the point that we're always guaranteed that we're going to be able to read database files from previous versions. So because our storage format's still changing quite frequently because of new structures, we ended up adding we didn't want to have this hassle of having to handle it. So currently, like if you change to, let's say 0.9, you basically need to do an export and an import of your whole database file.
And there's an estimate for that, calendar-wise? In the next 24 months?
The estimate was last year.
Oh, okay. So you're perfectly on time. Thanks.
Hey, so love the talk and the energy. My question would be about, first of all, the name, because it sounds like the focus is mainly on the compute, not the database part, but the Duck part is great. So that one, and does DuckDB actually provide something or promises about fault tolerance? Because you said that you can spin up on the server and use it in production, in pipelines, for example. But what happens if there's a faulty data point in the stream of data that is coming. So how does it handle that?
Yeah, so for the first question about the duck, yeah, I mean, the reason it's called DuckDB is because, you know, ducks are quite versatile. They can fly, walk, swim. I'm joking, guys. This is a corporate answer. The real reason is because one of the co-founders, the guy lives on a boat. So because of that, he didn't really want to have like a dog or a cat. I guess they're not great swimmers. So he thought that a duck would be a perfect pet. So he acquired a pet, or he adopted a duck while the duck was still growing. And when the duck, of course, became adult, went to live its own life. But he grew very fond of his duck, and he wanted to name his system DuckDB, and that's the real story. About the fault tolerance. So we do have, for example, checksums in our storage to guarantee that the storage is not corrupted. But there are definitely errors that could still happen that could potentially corrupt your data. But we do have some more basic checks on it.
Even in the middle of the compute, for example, if I have 1 million rows and it fails on the 900,000 one, do I need to do it all over again?
Yeah.
Okay.
Yeah, basically this will most likely throw some kind of exception, and then you have to re-execute it. Okay. I mean, I guess you can have some kind of caching mechanism around that, but we currently don't.
Cool. Thanks.